welcome back, guys. Today we will discuss yesterday we completed the phase one of our DevOps and mlops project, right? Now, today we will discuss start phase 2. Okay. In this phase, we will discuss about DevOps mostly. Okay. DevOps first part. Okay. In which we will discuss about the containers and CI/CD pipeline, and we will discuss about cloud and IAC. Okay. So today, what we will discuss? We will discuss Docker. Okay. So the status for repo so far is like this, as you can see here. We have this install label package, which is review radar, okay, in SRC, and we can import it anywhere in our project, right? And then we yesterday in this app UI we build the stimulate app, right, in here, and we have this TOML file, right, which is talk about all the dependencies, right, in a very abstract way. Then we have requirement.txt, which mentions, list out all the dependencies with all the modules with their version, right. We have .env file, we have .example also, we have gitignore file also, .gitignore, right. Then so our plan today is we will discuss this Docker container, okay, and you see, today plan we must ship today our API, which is running inside a container, right, and this API will run inside a container, okay, and it will respond to our curl requests, okay. So welcome to phase 2, guys. Okay, DevOps is beginning today. If we do the quick recap of phase 1 finale, and so in that we discussed Postgres SQL, which will remember every prediction of ours, right? And Streamlit will give our model a phase, and we demoed that also for loop. Okay, which go through from UI to API, UI to API to model, then to database, right? So that was the flow. Hello. So let's do the homework first. Okay. So here you can see right now your UI probably shows the last 10 predictions here, right? So as you can see, if I run this here, right, first I will activate the right. and this one also. So before running this, I have to run the database first, PostgreSQL, right? So let me find the command from yesterday, which was this. Wait a minute. Sudo u postgres psql. It is where no. Going it like this. Yeah, that's the command. So sudo systemctl start postgresql. So I will run this sudo systemctl, right? Start, okay. Sudo systemctl start postgresql. Right, it's asking for my password. Alright. So this is started behind the scenes, right? Now I can run this Streamlit app. Streamlit run app/ui.py. What happened? Okay, so source venv bin integrate. Now I think Streamlit run ui/app/ui.py, right? I think now it's running here. Yeah. So as here you can see, guys, it's showing the last 10 1 2 3 4 5 6 7 8 9 10, right? Total is 12, but it only showing 10 reviews, last reviews, right? But what I'm saying is, what if you only want to see negative reviews, right? So you need filter in that case, right? So what we can do, we can add a select was in Streamlit, okay? So it could be like this. So what we can do is we can add here this selection filter. Okay, so choice is equal to streamlet dot select box. Okay, so it will be like so reviews. Okay, it will like all, or it can be like positive, right? It can be filter, like you want to see all, or you want to see or positive, or you want to see negative, right? Like this. Then what can happen is so as you can see here, I think if I do this, as you can see here, we have this filter already, right? Yeah, filter box is there. So here we have this get stats, right? And get recent prediction limit is 10 here, right? Like this. So we have to change it to so we have to give this function like this. Where we find this function is in review radar, right? Review radar db.py. So we go in here, we go and we go in the get recent predictions, right? So one more parameter it can handle is which sentiment like this, which will be string type and default will be all, right? Like this. Now here session query prediction ordered by, okay, so we have to so we have to pass some conditions, right? Then alright, so what we can add is query is equal to session dot query, right, prediction here like this, and then after that if this sentiment, right, equal to let's say positive, right? In that case, query will we will add the filter, right? Query dot filter predictions dot sentiment equal to positive, right? Here elif sentiment is equal to negative, right? So we are filter out the query equal to query dot filter here, right? And then we have prediction sentiment. Prediction table is the sentiment, is a column is equal to negative, right? Like this. If it is not, then what we can return is list of query dot queries already there, and what we can do is we will run this at filter query, okay, like this. Now what happened is alright. Now in this, what we have in our UI.py, here we have this for loop, right? P in the getters and prediction limit. So what we can do with it is we can send sentiment is equal to choice. What we already choice, we have choice, right? And now let me see what happens here. Okay, refresh it. Okay, so there is nothing there, and if I positive, 11 positive, so it's some error, right? Okay, let me see here what is the error. So it's sentiment, right? Already there, but sentiment. Okay. Uh, I think I need to rerun this DB again, right? Because my code is like this. I think now it's resolve this error. Now it's because the error it is showing, it should not be showing. It should not be showing this error, right? Because we already giving this get sentiment here, right? Sentiment. It's like this. Sentiment negative, positive, negative, like this. Everything is there, right? And then we also passing this choice. Okay, let me do this only. What? sentiment here it is. It's resolved in white. Okay, so I think I need to streamlit run app UI API. Right. Yeah, there is no error now. You can see, and if I want to see positive only, this is only showing positives. If I want to see only negative, it's only seeing negative, right? So our filter by default it's working for all. Alright. So this is very important, guys. Now let's start alright. So let's discuss some theory for before everything, right? So let me show you the problem we will kill today, okay? The problem here is, guys, to run review radar right now, watch what I need to do, right? So what I need to do, I need to, as you can see here, I need to run this database first, right? In one terminal. In second terminal, I can run the to add some reviews. I need to run fast API like this, right? In terminal 3, I need to run this review radar streamlit, right? So 2-3 terminals I have to run. One for database service and the virtual environment variables, and the right Python version, right? Now imagine you clone my repo on your machine. Okay. Different Ubuntu versions are there, different Pythons on your systems, right? Maybe no Postgres you have, right? Will it run on that? It cannot run, right? Maybe. That's it. That works on my machine today. Okay. It may be not work and maybe work. So we have to remove this maybe from this here, right? So in 2013, a small company called .cloud. Okay. There was a small company called .cloud. Okay. So it open sourced an internal tool named the Docker. Open source the Docker tool, which was the internal tool of their, okay. And within 3 years, it revived how the entire industry ships software. This is the case for 2013, guys. Not exaggerating for you. Pre-Docker and post-Docker are different eras you can use. Okay. So the promise it does, it packages your application. What is your application? Your application has code. Your application has dependencies. Python itself, system libraries, everything, right? This all come together and make you an application. So what it do, it will package it into one sealed box called a container image. Okay. What it will do, it will take your application It will take your code, libraries, right? You can say system libraries also, pillars, Python, your Python itself, right? What version you are using, Python, and plus dependencies. It will take everything and cover it in a package. Okay, this package called container image. Okay, that image will run identically on my laptop, your laptop, your cloud server, a Raspberry Pi cluster, same bytes, same behavior everywhere forever. That is Docker for you. Okay, this is very important. Like one binary you will have and it will run on every machine. Job relevance for to understand Docker. So Docker appears in essentially every DevOps posting, okay, and a huge share of ML postings also. It's like assumed like Git. You are being expected that you will know like Git, Docker, Kubernetes, okay. So these are the biggest infra skills of the decade, okay. So on day 70 literally exists to run containers. No Docker understanding, no Kubernetes you will can understand, okay. And every CI/CD pipeline we will understand on 12 day of 12 and 13 there, that will build and ships images only, okay. So today is the load bearing day for us, right? By end of this stream we will install the Docker and will understand it, and our API will running inside a container only for now, okay. And optimized multi-stage image, you will understand also what is multi-stage also, about half of the naive size, and security basics done right. All right, so here first concept for you is there was a shipping container story, right? So like this is the actual origin of the metaphor for Docker, okay. Before 1956, loading a cargo ship was very chaotic, okay. Barrels, crates, sacks, every item handled individually, right? Every port different loading took days, right? Things broke and vanished in the process. Then Malcolm McLean standardized the box, okay, the shipping container. So all the boxes will have same dimension, same corner fitting worldwide. Suddenly any crane could move any container between any ship, train or truck, right, without ever opening it or carrying what's inside. Then the global trade exploded after that. Same in software had the same QoS. My app need Python 3.12, these 40 libraries and this system package, and these environment variables like this, right? And every server is a different port with different equipment, right? So you can assume Docker is McLean's box for software. It standardized the container, and any machine that runs Docker can run any container without caring what's inside the container, right? A logo of this Docker is literally a whale carrying shipping container, okay. So one thing I mentioned two terminology here, right? Image and container. So what is image versus container, right? Image with container. What's it? So these are two words you must never confuse about them. So you can use an image is a frozen recipe with ingredients. You can look like this. Frozen recipe with ingredients. Okay. In technical terms, it's just a read-only snapshot of a file system plus instructions. Okay. Like instructions are like start from this OS layer, add Python, add these libraries, add by code. When launched, then run this command, a file, right? You can say it's a file, effectively shareable, okay, and versionable also, and immutable also, because it is read only, right? While the container is you can say uh, it's a file eventually, okay, and this file is versionable and immutable. This is the image for you. Now, what is a container, right? A container is running instance of an image. A running instance of an image. You can like a dish actually which is cooking. Okay. One image can spawn 100 identical containers. Right? You have ingredient, you have recipe, and you can cook 1,000 of meals, right? Like it should on day 3 image is the class and container is the object, right? Okay, so you remember that on day 4 we had the frozen data class, right? Which there was immutability as safety in the data class, right? An image is always immutable. You never patch a running container inside a production, right? What you do, you build a new image and replace the container. That's the principle. That principle also has a name, which is called the uh, infrastructure, immutable infrastructure. Immutable infrastructure. Okay, and it's the philosophical core of modern DevOps. I told you that moment would come back always. Okay, how containers actually work, and they are not virtual machines also. Okay, So you can be confused between uh, virtual machines and Docker container. So that's a very important interview question you can encounter in your interviews, right? And you have to understand this very uh, sincerely and in detail. Okay. So imagine what problem are virtual machines solving actually. Okay. Virtual machine. What are they solving? So imagine you have one physical computer. Okay. In that physical computer, you have CPU, you have a RAM, you have a SSD, right? Now, suppose two companies want to use the same computer. Just a minute, I will be back in a minute. Now guys, we have this, right? Yeah, what we were understanding was this. See, yeah, we have virtual machine like this, right? No, we were understanding. So this is your physical computer, right, at your home. Physical computer. Now let's say suppose two companies wants to use the same computer, right? Company A wants Ubuntu and company B wants Windows for that, right? Normally this is not possible because one computer usually runs on one operating system. Okay. So what happens? A virtual machine solve this problem. So what happens is a virtual machine pretend that one computer is actually many computers. So this is like you can write that statement: a virtual machine pretends that one computer is actually many computers. Okay. So what happens? Let me draw you a diagram. So you have a physical computer, right? You have this physical computer. What you have? Then you have this called hypervisor. You can say VMware, or you can say it virtual box, or you can say it KVM. Okay. Then what will happen? Then it will divide this one physical computer with this with the help of hypervisor in virtual machine 1 and virtual machine 2. In this virtual machine you can run Ubuntu operating system, and here on virtual machine 2 you can run Windows operating system, and here you can run some app, let's say app A, and here you can run some other app called app B. One more thing, each virtual machine think I have my own computer. Okay. This virtual machine think I have my own computer. The only one computer exists, which is me. Every virtual machine think that. Okay. And this virtual machine think there is only one computer exists, which is me. Okay. But and actually they are sharing one physical computer. Okay. Like this. And inside every virtual machine there is a complete operating system, right? As it is here, right? You have this operating system, Ubuntu OS and Windows OS in this virtual machine, right? So inside every virtual machine there is a complete operating system is there, okay, which contains kernel, drivers, system libraries, shell, system service, everything. It's a complete OS. Okay. Similarly, for in Windows 2 also contains a complete operating system. So you would have seen, or if you don't seen, I am telling you this, right? Virtual machines are very heavy. Okay. Why they are heavy? Like suppose Ubuntu is 2 GB, Windows is 2 GB, 5 GB, right? Let's say. Now virtual machine Ubuntu is 2 GB of storage, and this is of 5 GB of storage, right? Total is 7 GB for just for operating systems. Then add applications, they will become very large, right? And when you start a virtual machine, it behaves exactly like turning on a new computer. Okay, like what happens is it you power on, then it boots the BIOS, right? Then kernel, then drivers, then services, then desktop. This takes like almost 1 minute or 2 minutes, depending on the machine, right? Now, what is this hypervisor? You will be confused, like, okay, you are talking just about this virtual machine. What is the main thing here, right? So the hypervisor is the software that creates virtual machines. You can think of it as a virtual manager, building manager, right? So hypervisor will be uh, connected to physical computer and virtual machines. Okay. Now, what are containers? Okay. You understand what are virtual machines, and now understand what are containers. So Docker is a container, right? Right. So Docker asked, okay, do we really need three complete operating systems, right, to run our applications? Usually, answer is no. Suppose every application runs on Linux. Let's suppose, right? So why we need to install Linux three times? Instead, everyone shares one Linux kernel only. Okay. So, so everyone will share the Linux kernel. What happens is, this is the container architecture. You have this uh, application A, right? You have application B here. You have application C here, right? You have three applications, let's say. These all will go to the Docker engine. Okay. That Docker engine will connect to Linux kernel, and then you have hardware at the end, right? So you notice for all the apps there is only one kernel. Okay, just a minute. Alright, so that was it, guys. Uh, let's continue again. So notice there is only one kernel here, right? So what is the kernel? This is probably the most confusing word for you. Kernel is the core of the operating system. Think of Linux as a company, and CO is the kernel for you, and employee are the programs. Okay? The kernel will control CPU, memory, disk, network, USB keyboard, like this. Okay. So applications cannot talk directly to hardware, right? So everything goes through the kernel. So suppose Python wants to read a file, uh, then Python, this is a py file, right? Then it will goes to kernel, then it will goes to SSD, then kernel again, then it will come back to Python. So the kernel will perform the actual work, right? So why we need to share the kernel? Okay, suppose there is a host OS is for you is the Ubuntu OS. Okay, Ubuntu is our host OS, right? Let's see, and it already has a Linux kernel. So every container will simply use Linux kernel, right? So this is Ubuntu here. So we have Linux kernel, right? Linux kernel already has this Linux kernel, right? So in container we have different apps, right? Different applications, which are one is a Python app, one is a FastAPI app, right? And we have one other is Postgres app, right? This is container 1, this is container 2, and this is container 3. All of them will share this same kernel. Okay, nobody installed another kernel. That's why containers are very tiny. Okay, so in virtual machine we had something like 7-8 GB, right? But in container we only have, like, say this application has 200 MB, and libraries plus libraries of 100 MB, so total of like 300 MB only. So there is a huge difference between them, right? And container also start quickly. So what happens in virtual machine? They start, then they will boot the OS, their kernel, drivers, services, applications, like that. In container, just start and it will start running the process. Start and it will start running the processes. That's all, because the kernel is already running, right? So a container is just a Linux process. This sentence surprises many people, but you see, a container is just a Linux process. Okay, imagine you start one file Python in app.py, right? So Linux will create one process for this, right? Docker does the same thing, except that process is isolated here. Okay, normal process, what happens? No, normal process is Python can see everything. Okay, in container process, container processes are isolated. Okay, so Python only see its own environment. Okay, the application will think I am alone, but it is actually it is not. Okay, so there is a feature called namespace. Okay, namespace, this is the first Linux feature Docker will use. So imagine there is a hotel, and in the hotel there is multiple rooms, room 101, room 102, room 103, but guest is in room 101. So guest which is in 101, it cannot see room 102, right? So namespace works exactly like rooms. Okay, without namespace, container A can see container B processes. Bad. It is a bad habit, right? Bad uh, framework. But with namespace, container A will only see its own processes. Container B only sees its own processes. Each container believe I am the only application running here. Okay. So what namespace will do? It will it isolates processes. It isolates files, network also, and host name, also users. So each container will get its own view. And there is a concept called process namespace. Suppose host is there, right? So there is process ID is 1, system D, right? Process ID 200 is Chrome, process 300 is Docker, right? So inside container, process ID 1 is fast API. That container will think fast API is the process number 1. It cannot see Chrome. Okay. File system namespace right. This is how we isolate the processes. Okay, different process and only see the its own thing. Okay, next thing is file system, right? So file system namespace, let's say on host you have the /home /Sunil, right? You have two folders, downloads, you have documents. You have two folders, right? And there is a container called / under this you have app, you have requirements .txt, you have main.py. Okay. So this container will believe that its file system start at this /. Okay, this / only. It does not know about document folder or download folder. Okay, like that. And a network namespace, what is this? Let's say container A. Okay, container A is localhost and is very different from container B localhost. Okay, each has its own network. All right. And also there is a concept called C groups. Okay, C groups. What is this? So namespaces will control what you can see. Okay, but C groups will control how much you can see. Think of it, electricity. Suppose three apartments share one building, right? Owner says apartment 1 can maximally use 2 kV, kW, 2 kilowatt, and apartment 2 can use maximum of 3 kilowatt. Nobody can use unlimited electricity. So that's the C groups. Okay. How much you can see? So suppose laptop has sole 16 GB RAM, right? Docker can say, okay, container A will maximum use 2 GB, and container B will maximum use 4 GB, like this. So no container will exceed its limits. That's the rule. So this is important because suppose one application has a bug. Without C group, it can use 100% memory, right? It can fill all the memory. In computer, your computer will freeze. But with C groups, application uses only 2 GB and stop. So your computer will survive from freezing, right? Why Docker won in the end? Imagine you have a laptop and you install a virtual machine there. With the virtual machines, what you have? You have Ubuntu, 2 GB Ubuntu, right? 2 GB Ubuntu, and you have 5 GB of Windows, right? And 2 GB of Central OS, okay? Very quickly memory is exhausted for you, right? But in containers, what happens is in container you have a fast API app which is 150 MB only. You have Postgres 300 MB. You have Redis, let's say 50 MB only. You have Nginx, you have 30 MB only, right? So you can run dozens of containers simultaneously, right? So there is a famous sentence: virtual machine will virtualize the hardware, but containers will virtualize the operating system. Okay. Okay, you understand this Docker virtual machine, right? Container. Now let's understand next concept, which is layers. Okay. This is one of the most important Docker concept. Okay. If you understand layers, okay, you will understand why Docker builds are very fast. So let's go through every single sub concept of this concept. Okay. So you see the images of the app, right? Images are built in layers. Okay. So you understand what is an image? It is a snapshot, blueprint, or a recipe, right? Just a file eventually, right? So yeah, I told you like recipe is there because there is no instance of it, right? I explained it to you. Image, what is image here only, right? Here. Read only snapshot of a file system plus instructions. Okay. Eventually it's just a file only, right? Now you know the image already. What is the layer now? Okay. So imagine you are drawing a picture. First you draw the sky, right? Like this. Okay, these are the clouds, right? Then you draw some mountains like here, like this, right? Then some trees, right? Like this, you draw some trees. Then some people, like this, right? You draw some people. Like this. So you can see each drawing sits on top of the previous one. Okay. Docker also works exactly like this. Every instruction creates one new layer. Okay. Each instruction in the recipe adds, so in each instruction in the image. Okay. Each instruction in the image adds one layer. Okay. So suppose your docker file is this like this. Okay. uh, your docker file look like this: from ubuntu run apt install python 3, and then copy requirements .txt, then again run pip install requirements .txt, and so okay. So what will happen? Docker will not make one huge image of it. It builds layer by layer. Okay. So layer 1 would be like this. Layer 1 will be like this. Okay. From Ubuntu only. This is your layer 1. It will create layer. This instruction will create Ubuntu layer. Okay. This will contain okay Linux plus shell plus basic utilities, right? Like this. Then layer 2, you have this command called run apt install python 3. So now Docker will add another layer. Okay, like this. Python is installed, right? Like, let's say like this. So you notice something here. Docker doesn't rewrite Ubuntu. Okay, it simply adds another layer. Then layer 3 and adds requirements, right? Then layer 4 and so on, right? So you understand the layers. What is the genius concept here is? So genius concept is, genius here is all the layers. You understand? Layers are shared. Okay. Suppose you have project A and project B, right? Both use this, like say you have project A and project B, and both uses Python 3.12. Without sharing, project will create Python 500 MB for Python, and project B also take 500 MB, total 1000 MB, right? But Docker says wait, they are identical, so you have to just store only one copy, right? So project A and project B will share this same Python layer. Okay, 500 MB only. So this is huge memory saving right here. And one more thing, layers are shared. This is one concept. Another concept here is layers are cached. Okay, what is this? Layers are cached means? Cache means save something so you don't have to do it again. Suppose today you build your Docker image, right? So Docker stores this. You build your image, right? So Docker will store this Ubuntu layer. Ubuntu layer is there. You have Python layer there, right? Then you have a requirement layer. you have the code layer also. Okay, let's, and tomorrow you change this main.py. If you change main.py only, so should Docker reinstall Ubuntu again? Answer is no, nothing will change. Should Docker reinstall Python? No, no reinstall of library, right? Only code layer is changed, so Docker rebuild only that layer. Okay, Docker only rebuilds code layer. Okay, like this. So this is why Docker builds become very fast. So it only build the changed layer, right? Also, there are few more rules in Docker. Right, rules are like this. Rules are like this: is order your Docker file from least changing to most changing. Okay, so this is one of the most important Docker rules. Imagine your project. What changes least? Ubuntu, right? Almost never. Python version rarely changes. Libraries sometimes changes, but your code changes every day. So your Docker file should look like this only. Look like this. Okay. So notice here your code is coming last, right? Why? Because suppose you edit like code from code file, right? Docker will check Ubuntu is same, then Python is same, right? It is same, libraries are same requirement, right? Code has changed, so only it will rebuild the code, right? If it is wrong order, right? So let's say if your code is here, right? And now your code is copying like here. Let's say we'll let you go to the same for here. Copy code. So this command is, let's say, here, right? So before the requirement, you are copying the code files, right? And tomorrow, let's say you edit one Python file, okay? Then Docker will check, okay, this file has changed. So everything after that must rebuild, right? Now it will reinstall all the libraries again, even though libraries never changed, okay? So the correct order will be Ubuntu, then Python, and libraries, then code, okay? So why this order matters? Why does Docker do this, right? So Docker assumes every layer depends on the previous layer. If layer 2 changes, then layer 3 may also change. So everything after it must rebuild. So think of a house like foundation, then walls, then roofs, right? So if you rebuild the foundation, you cannot keep the old walls. You rebuild everything above it. So Docker also works exactly the same way. Okay. So may encounter a question. Okay, suppose why do we copy requirement.txt before copying source code? So what will be your answer? Because the dependencies change much less frequently than source code. Okay, and Docker caches the dependency install layer like this, right? Okay, let's move further. All right. Uh, so next concept for you guys is the registries. Uh, Registries. You can understand it like it is just a GitHub for your images. All right. So where do our images live, right? So you know what is images, right? So earlier we have already learned this image, right? What is images? So image is just like a packed application here. So now the question is, where do we store these packed images? You can say applications. The, so we store them in a registry. Registry. So what is this registry? So think about Git, right? Where do you store your code? On your laptop. Then from your laptop, you push it to GitHub, right? So your GitHub will store the source code. Similarly, where do Docker images live? So Docker images live. One is on your laptop. Then you go for Docker registry. Okay. So this registry will store your Docker images. So imagine you have baked a cake. Okay. So you bake a cake, then you put it in a bakery display, right? Then from there, customer will buy it. So what happens is Docker works very similarly. First you build the image, right? build image, then push it to registry. Okay, now anyone can download it. Okay, so this is the Docker Hub. The public default is Docker Hub. Docker Hub is the largest public registry out there. Okay, this is very default, and think of it as like a GitHub for Docker images. Okay, millions of Docker images are stored there, like for example Python, Ubuntu, MySQL, PostgreSQL, Redis, Nginx, right? So when you write from Python 3.12 slim, right? So where does it come from? It is Docker. What happens is Docker automatically downloads it from Docker Hub, unless you specify another registry. Okay. So what happens? The flow will be like this. In a Docker file, you have this from Python 3.12 slim. So what happens? It goes to Docker Hub, like GitHub, right? And then it will download the image of Python. Okay. The next thing for you guys is GHCR. What is this? On day 13, CI will push our image to GHCR. GHCR means GitHub Container Registry, right? So GitHub will now store the source code and Docker images. For example, so you have this GitHub repo. You have called review radar, right? But in GitHub container registry, which is GHCR, you will have this review radar image. Okay, everything will stay inside GitHub for now. Okay. And what is CI? CI, you are heading it, it's like continuous integration. Okay, so imagine this workflow. What you do, this is you do git push, right? This goes on GitHub. What happens then? It will automatically builds the Docker image on the changed code, obviously, and then automatically upload the image. No manual work here. GitHub Actions does it automatically for you, right? Next thing is image names. So what image names tells us? In very simple language, image names encode their home only. Okay. So image names have a standard format which is like registry name colon tag. Okay. Let's understand each part here. So let's say for registry you have this docker.io or ghcr.io. Let's say this tells Docker where the image is stored in which registry, right? Okay. And the name is just this example. It can be Python or your review radar. Okay. Like Python or review radar, it can be. So this tells the image name. And tag, and this tag is 3.12 shilling for this Python, and right, and let's say v1.0 like this. So tag represents the version, right, like this. So version is very important. And one most important instruction you must follow: never trust latest in production. Okay. Suppose today this is latest is version 1, and tomorrow someone uploads version 2, right? Now version 2, right? So now latest is version 2, right? So your application suddenly changes. You didn't change anything, but Docker downloads a newer image, right? Very dangerous here. So instead, always use like specific versions, right? Now your builds are reproducible, and next thing computer is like, guys, for you is multi-stage builds. Okay, what are these? So imagine you are building a wooden chair. Okay, to build it you need hammer, you need a saw, you need a drilling machine, right? You need a screwdriver. After the chair is finished, do you deliver the tools with the chair? No. Customer only needs the chair, right? So Docker also works exactly the same way. So build stage is there. So build stage you need compiler, first stage build tools, development libraries, right? So at first stage you need a compiler, you need some build tools, right? And you also need some development libraries, right? So these are needed only while building the image. There is a runtime stage also. Okay. So this is build stage. Then you have the runtime stage. Okay. After building, only the application is needed. Okay. So you need application, you need Python, you need libraries, no compiler this time, no build tools, right? So because why we do that? Because suppose a compiler takes 700 MB and application takes 120 MB. Without multi-stage, image will take 700 plus 120, 820 MB with multi-stage, right? But with multi-stage, final image will take only 120 MB, which is much smaller. So smaller image, suppose internet speed of 10 MB per second, 800 MB will take 80 seconds and small 120 will take 12 seconds only. So it's a huge improvement here, right? And this Docker is smaller attack surface. What does it mean? Smaller attack surface, right? So attack surface is like how many things there are that attacker can exploit. So imagine a house, right? House A has 20 doors and but house B has only 2 doors. Which is safer, right? Obviously B is safer. So Docker image also works similarly. More software, you have more bugs and you have more vulnerabilities, right? But if you have a smaller image, you have less software, you have fewer vulnerabilities. So why not run container as root? There is a very big question. Why not run container as root, right? So this is very common interview question. What is root, right? What is root? Root, let's understand this. So Linux has a super user which is root. Okay, what root can do? Root can delete files, install softwares, right? It can change password also. It can shut down the system, right? It has unlimited permissions, right? So suppose your container runs as root, your application is get hacked, right? So root can do anything very dangerous in this case. So container escape normally. So container cannot access host, but occasionally security bugs are discovered. Yeah? So these are called the container escape vulnerabilities. Suppose an attacker escapes. If your container runs as normal user, attacker gets the limited permissions, right? If container runs as root, attacker may gain root access and very dangerous it is. So this is the least privilege principle for you. So least privilege applies the container inside the containers too. So this is one of the most important security principle. Give programs only the permissions they need. Okay, like this. Right, so this is your entire Docker workflow for you. Okay, uh, from writing code to running your application, let's understand every step here. So this is Docker workflow for you. You will have the Docker file first, then it will goes to the Docker build. Okay, then you have Docker image, then you have Docker run, then you have the container. Okay, so what is Docker file? So a Docker file is just a recipe or a instructions manual that tells Docker how to build your application, right? So Docker files look like this. Let me tell you this, right? Docker files contains, let's say for example, this is Docker file for you. Example is like from Python 3.12 slim, right, like this, and you have working directory like this /app like this, right, and then copy require UIRE requirements.txt, right, then you will have run pip install, so like this, right, pip install r requirement.txt like this, then copy. So every line tells Docker what to do, right? Then step 2, you have Docker build. Then you have Docker build, right? This command tells Docker read the Docker file and create an image. So it's like this. Docker then build t review radar. So this is like run the Docker program. This is for this build, then build an image here. T review radar tells like give the image name review radar like this. Okay, and at the end you have the dot also. So this dot tell use the current folder where the Docker file is located. Okay, so this is the location for the Docker file, right? Then step, this was second step. Then third step is Docker image. So a Docker image is a finished package. Okay, it contains your application, your Python, your libraries, your configurations, startup commands, everything. Okay, everything needed for the trip is like Docker image is the same idea. Docker image contains Python, fast APIs, SQL alchemy, your code, everything needed to run the application is inside, right? Inside that. Is the image running here right now? No. Image is stored only. Think of it as like a cake recipe. It is not cake, right? So similarly, Docker image is not running application. It is the package only, right? Then step 4 is Docker run. This command tells Docker create a running application from this image. Docker run review radar. For example, it can tell okay, Docker run review radar image, right? This is the name of review radar. So it will create a container, start the application, it keeps it running. Okay. Then last step is the container, right? So a container is a running instance of an image. So think of it as like a recipe. You will bake the cake similarly. Okay. Now, should we start coding for now or not? It's 11 already, right? Okay, thank you so much. We will meet you guys tomorrow after everything.